Good morning everybody, and welcome to today's worked exam answer video. In this video I'm having a look at a period 3 elements and their oxides question, which is one of the year 13 inorganic topics that follows on a lot from the period 3 work in the periodicity topic, which is taught in year 12. There is a lot, as with all inorganic topics, of content to learn, and a number of the things that we're being asked in this question are things that we need to be able to recall. There are some parts where we can apply some knowledge to minimize the amount of content we have to just rote learn, and I'll show you what those are, but there is a lot of knowledge here that I am going to be advising that you just learn. So as always, I'll annotate, I will write answers, and I will explain all that I am doing as we go along. So, first question is asking us to write an equation for the reaction of phosphorus with an excess of oxygen. Now, there's two key things we need to remember here. One, something that we learn in the periodicity topic in year 12, phosphorus molecules are made up of 4 phosphorus atoms joined together. Now, the mark scheme will allow you to just write phosphorus as P and balance the phosphorus atoms in the product by putting the balancing number 4 in the front, but P4 is technically more accurate. Second thing we need to remember is that phosphorus oxide, it can have a formula, an empirical formula of P2O5. However, P2O5 is not a stable compound in its own right, so we must always show this equation making P4O10. Phosphorus has an oxidation state of +5, the oxygens are -2, so P4O10. Do not simplify it to P2O5 because that is not stable and you will not get the marks. They're then asking us in part B to go on and explain how we would distinguish between this product, so the phosphorus oxide, and sodium oxide. So one of the key trends we need to know for our period 3 elements is that the metal oxides are basic and the non-metal oxides are acidic. And at that point, we should be thinking, well, if one's an acid and one's a base, I can test it with an indicator. We can use a universal indicator, as I have done. We can use something like litmus paper, that would also work. Or we could use a pH meter and get exact pH values. All of those would work. I've chosen to go with the universal indicator because I know the colours. When we're thinking about pH values, we would need to give those in a specific range, which may be harder to remember. In this question, they would have accepted the sodium oxide in water given a pH of 12 to 14 and the phosphorus oxide in water given a pH of -1 to 2, I think it was. And those numbers do, well, certainly for the phosphorus oxide in water, I have seen that value vary a little bit in the mark scheme, so I thought it was safer to go with the colours that the universal indicator would go in the presence of the sodium oxide and the phosphorus oxide in water. Sodium oxide in water creates a strong alkali, so the universal indicator will go purple. Phosphorus oxide in water will produce phosphoric acid, which is a strong acid, so we'll turn the universal indicator red. Now, it's really important that we add both of the oxides to water before we then test with the universal indicator. If you don't recognise that these solids need to be turned into solutions for us to be able to test them, you will be penalised. Okay? Another really common question for period 3 elements and their oxides is thinking about the structures of different oxides. So it says crystal structure, which may be slightly confusing. It just means structure in relation to structure and bonding. So silicon dioxide is one of the 3 giant covalent structures we need to know, alongside diamond and graphite. Sulfur trioxide, thus simple molecular. And as an extension of that, we are then asked to explain why the silicon dioxide will have a higher melting point than the sulfur trioxide, which all comes down to their structures. Within the giant covalent structure, there are many strong covalent bonds. These are going to take a lot of energy to break. Now, because it's a comparative question, because it's asking us why it has a higher melting point, I've said that those strong covalent bonds would take a lot more energy to break by comparison with the weak intermolecular forces that will be present and overcome with our simple molecular SO3 structure. Yes, this does contain covalent bonds, but with any simple molecular structure, we are not breaking covalent bonds, we are overcoming the weak intermolecular forces. And because they are a lot weaker, that takes a lot less energy for those forces to be overcome. And it is a comparison, so you do need to make it clear that either one takes a lot of energy and one takes little energy, or one takes more energy, using that comparative language. On to the final 3 questions. I think this is where we can potentially use a little bit more application to help us and perhaps not need to rote learn all of this detail. As in, we don't need to necessarily rote learn the whole equation. So in part E, we were asked to write an equation for the reaction of sulfur trioxide, which is acidic, with potassium hydroxide, which is basic. When we react an acid and a base, we get salt and water. So after I'd written out the formula of the SO3 and the KOH, in terms of the salt, we were going to get potassium sulfate and water, and at that point it just became a case of balancing that. So 2 potassiums in my potassium sulfate salt means I need 2 lots of KOH, which also then balances my oxygens and my hydrogens as well. So the key, I guess, general equation to remember there is acid add base makes the salt plus water. For the next equation, again, we can use a general equation to help us. So in this one, we're writing an equation for the reaction of magnesium oxide with phosphoric acid. So magnesium oxide being a metal oxide, whenever we react a metal oxide with an acid, we make a salt plus water. So we do need to know the formula for phosphoric acid, which is H3PO4. And we then need to be able to work out A, what salt is formed, so magnesium phosphate, and B, be able to write this formula. So within the phosphoric acid, there are 3 protons, which are each +1. That means this phosphate ion has a charge of -3. If the magnesium ions are +2, in order to balance the +2 of the magnesium and the -3 of the phosphate ion, we're going to need 3 magnesiums and 2 of the phosphates, which need to be in brackets because the phosphate ion is made up of 2 different elements. Then we've got our water, and then it comes to balancing. So the 3 Mgs balanced by putting 3 in front of the MgO, the 2 phosphate ions balanced by putting a 2 in front of the phosphoric acid, and then the additional water that we get, the additional oxygen that we get from the 3 magnesium oxide goes into the water. So we need 3 of those as well, which also balances out the hydrogens that we get from our phosphoric acid. So if you are comfortable working out the formula of a salt and you're comfortable with writing formulae and balancing equations, those general equations might be all that you need to remember here. And then finally we're asked to draw the displayed formula, which is going to come in handy because we've got OH bonds, which some people forget we need to show the bond between the oxygen and the hydrogen in. So displayed formula of the undissociated acid, so not when it's given up a proton in its full complete form, and we're looking for the acid that is made when sulfur dioxide reacts with water. Now, it is sulfur dioxide reacting with water that makes this version of sulfuric acid. We would still call it sulfuric acid. The only difference is the oxidation state of the sulfur here is only +4, whereas the usual H2SO4, the sulfur has an oxidation state of +6. Now, H2SO4, that version of sulfuric acid is made when we have sulfur trioxide reacting with water. So if it's sulfur dioxide, we get this version of sulfuric acid, and it will say sulfuric bracket IV, the Roman numerals, acid. And if we are making H2SO4, that would be sulfuric bracket VI acid for the Roman numeral +6. So then we've got to draw this. Now again, you should be already familiar with the formula of H2SO4 from some organic reactions across the course. H2SO4 would have 2 OH bonds coming from the sulfur, and it is that OH bond that we manipulate and use in electrophilic addition mechanisms of alkenes reacting with sulfuric acid. We also need to know the structure of this potentially for the dehydration reaction of an alcohol to an alkene where sulfuric acid is used. If it was H2SO4, you'd then have 2 double bonds to oxygens. So when we don't have 4 oxygens and we only have 3, it's one of the double bondos that gets removed. And because sulfur has 6 electrons in its outer shell from a shapes perspective, thinking about how many of those it's using in these bonds, it's using 1, 2, 3, 4. There's 2 non-bonding electrons which give us our lone pair. The lone pair is not essential, but I do think that it makes sense to include it because it shows that you're thinking about the possibility for this to be H2SO4, and obviously those electrons would then go into forming that double bond with the additional oxygen. If it's not there, having the lone pair makes sense to me. So that would be our displayed formula, because I've showed all atoms and all bonds of this acid before it dissociates. Now this is quite a weak acid by comparison to the normal sulfuric acid, H2SO4. So this will only weakly dissociate into H plus and HSO3 minus, whereas sulfuric acid will completely dissociate. The usual H2SO4 sulfuric acid will completely dissociate into 2H plus and SO4 2 minus. So a lot of information to learn, some questions that you should be able to answer using your knowledge from structure and bonding. These are not specifically period 3 elements and their oxides questions, which is nice. Some questions that you can work out by knowing some general equations, and certain equations you will find come up a lot and certain comparisons will come up a lot. And I was having a look through a variety of different questions, and the number of times this equation came up and some sort of comparison between this and sodium oxide, how that's made, the comparison of one being basic and one being acidic came up. It came up a lot. So definitely some key things to learn. Anybody got any questions about anything that I've mentioned in this video or anything else to do with period 3 elements and their oxides, please do get in touch. Hopefully that's been useful, guys, and I will catch you all soon.